Now we'll discuss differentiation. That is, we have briefly discussed this before, or the idea behind this, when we studied coordinate geometry. We define the slope of a straight line and then observe that other curves do not have constant slope. In fact, we define the straight line as the curve having constant slope. Correct? So, when we started this topic of calculus, I told you that if you look at other curves like parabola, for example, they do not have constant slope. However, we can still discuss the idea of slope for the other curves. For example, if you have a parabola, you can still discuss the steepness of this curve. As I told you, if you imagine you are climbing this from here, if you're climbing this as a hill, for example, you can imagine that as you go forward, the difficulty is more and more. You require more and more effort as you go forward to climb up. Right? And that's because the slope is increasing, the steepness is increasing. So the slope itself is now a function of x. The x position at which you are standing, or the x coordinate of this curve, right, for every point xy, the slope is a function of that x. So that's why when you say the more you go forward, the steeper it becomes. What you're saying is, as a function of x, the slope is increasing. As x approaches, or as x increases, the slope also increases. But now we want to say exactly what the slope is in terms of x. Okay. So for this, you need a more general notion of slope, which doesn't apply only to straight line. You want it defined formally. So in the case of straight line, what we did was you measure the rise upon run, correct? The difference in the y coordinates, which I will denote by delta y. So that is y2 minus y1. So this point is say x2 y2, and this first point is x1 y1. Then this delta y is y2 minus y1. Similarly, the difference in x, that is x2 minus x1. So the slope of a straight line is y2 minus y1 by x2 minus x1, as we know, and that this other notation, it is delta y upon delta x. What if you have not a straight line but some other curve? So we can still do the same thing. Wait. You can still look at what happens if you go forward. So here you have one point in the curve, that is say x1 y1, another point x2 y2, and then in the same way, with the same formula, you can find delta y and delta x. The formula remains the same, nothing different there. Okay. The problem is this is no longer constant. For a straight line, this will be constant, which means you can take any point x1 y1, any other point x2 y2, and this value that you get, this delta y upon delta x value that you get, that will always be the same no matter which two different points on the straight line you take. But on the on any other curve, it is clear that this will keep changing. So here, this is the slope. So for example, take a more extreme example. Suppose this was the curve. So if you take 2 points here, x1, y1 and x2, y2, then here the change in y is 0. If this is perfectly parallel to the x-axis, change in y is 0. So here delta y by delta x is 0. Delta x is there. We are increasing x. So we are taking 2 distinct points. But still the y is not changing. So delta y by delta x is 0 if you measure it with these 2 points. Whereas over here, clearly it is non-zero. You have some delta y which is not 0. So delta y upon delta x is also not 0. So not 0, I mean. So these are different because you measured them at different parts of the curve. So that's what is going to happen here also. As you measure the slope at different points, the slope is going to change. So what can be the definition of slope if it is not at all constant? Well, we can talk about the slope at this point, at a single point. But how does it make sense to find the slope at a point? Because we need at least 2 different points, right? In fact, we need exactly 2 different points in order to find the slope. So how can we find it at one point? So that is where we use the idea of limits that we have been developing in the previous few sessions. So we want to find it at one point, but it is not defined at a single point. So just like those functions, for example, that the first function that we looked at, x square minus 1 upon x minus 1. This is a function that is defined everywhere except at 1. So it is not defined at 1. Nevertheless, we were able to find its limit as x approached 1. And we could say that this approaches 2 as x approached 1. So in the same way, we want to find the limit of this as the second point x2, y2 approaches the first point. So if we found the limit of this slope delta y upon delta x as the second point approached the first point, then that would in some sense be the slope of the curve at the single point. Okay. Although obviously the definition of slope requires 2 points, we can find it as a limit and say that that is the slope of the curve at a point. So let's try to do that. So we'll take an example first. That is y is equal to x square. Simplest, maybe the simplest example where the slope is not constant. So now we need to take 2 different points. So x1, y1 and x2, y2. But now we don't have to write them as some unrelated 2 coordinates anymore, because this curve is given by the equation y equal to x square. So y1 is not independent from x1. If we know x1, the value of x1, then in terms of x1, what is the value of y1? It must be x1 square. Similarly here, y2 must be x2 square, right? And let's call this as before delta x, and this is delta y. So what we want to find is delta y divided by delta x, but not in general. We want to find it as the second point. So as x2, y2 approaches the first point x1, y1. We want this limit. I hope the geometry here is clear. Again, this is not very easy to compute because we are writing in terms of points. But you can see that when will x2, y2 approach x1, y1? When this difference delta x approaches 0, right? Or equivalently, x2 approaches x1, same thing. Because y is completely determined by x. Y is always equal to x square. So if x2 approaches x1, then y2 will approach y1 at the same time. So you don't need to really write it as this point approaches this point. That's equivalent to writing just the x coordinate, the second x coordinate approaches the first x coordinate. Or equivalently, the difference between the two x coordinates approaches 0. That's what we want. Now, in order to again evaluate this, we need to know what is delta y in terms of delta x. Okay, one thing here, if you are not seen this notation before, you might be confused what is delta. We are just using the notation delta x to denote the difference in the x coordinate. So delta denotes difference. It is not a separate constant or variable. Okay, delta x is one thing. This delta x is one. You should understand it is one thing. It's not delta multiplied by etc. This is just the name. Okay, in case you have not seen the notation before. So there's no question of cancelling delta, for example, in this fraction, right? Okay, so we want delta y in terms of delta x, but we already written what what is delta x? It is x2 minus x1. And what is delta y? y2 minus y1, right? Now, okay, if delta x is x2 minus x1, we can write x2 is equal to x1 plus delta x. That should be clear. And therefore, um, delta y, which is y2 minus y1, is equal to, now what is y2 in terms of x2? y2 is x2 square. So this is x2 square. y2 is x2 square minus y1 similarly is x1 square. Right? And x2 from here is x1 plus delta x the whole square. x2 is x1 plus delta x, so we are squaring that. And then we're subtracting x1 square. So simplify this. A square plus b square. So I mean a plus b whole square. So a square is x1 square plus 2ab. So 2x1 delta x plus b square. So delta x square. So this much is from the expansion of this. And then we have this x1 square. So this first term gets cancelled with this last term. And we only have 2x1 times delta x plus delta x square remaining. So what we want to evaluate is this. Now, as you can see, this numerator is what we have evaluated here just now. So that is 2x1 times delta x plus delta x square divided by denominator is the same, just delta x. Here what is common? Delta x. So this is limit delta x approaches 0 of 2x1 plus delta x, and that is equal to just 2x1. Okay. Apart from the notation of using delta x and delta y, everything here is what we have done before. We have evaluated limits like this, right? So this is really no different. It's just the notation is we are using delta x instead of just x approaches 0. We are saying delta x approaches 0 and x1 is some fixed constant. So is the evaluation of this particular limit clear? We're going to do this in more generality, but is this example clear at least to everyone? I mean, obviously, if you've studied differentiation before, you have seen all this. Okay, so did we actually find the slope as a function? What we did was take two particular points, x1, y1 and x2, y2. However, we have not fixed the values of x1, y1 to some specific numbers, right? We fix them as unknowns, so that's different. So we're not taking numbers like 1, 2, etc. So this x1 could be any x in particular. This could be any x. And so y1 would be appropriately that x square. Similarly, x2 and y2, but x2 and y2 don't matter really because they are approaching. We're going to find the limit as the x2, y2 point approaches x1, y1. So all that matters is what is x1 because everything else is determined in terms of that. And the final answer also is just 2x1, clearly a function of only x1. Right? It depends only on x1. So in general, we can say limit as delta x approaches 0 of delta y by delta x well, not like this. This one at the point xy is 2x. Okay, where y is x square. Not for all the functions, for this particular function y equal to x square, for this particular curve, this particular parabola. Okay. So this means this, when I put brackets here and say xy, means when you are evaluating this at the point xy. Okay. So we'll look at more examples, but let me now formally define differentiation. So again, this is just some new notation for what we already saw. So the derivative of a function, if you have a function y is equal to f of x, then we define the derivative of the function y equal to f of x as dy by dx. So this is only notation. Sorry. This is just notation. Okay, again, as with delta, this d is not any separate variable and we are not going to cancel that anywhere. dy is the notation, dx is the notation. In fact, dy by dx together is the notation for derivative, and it is defined as limit as delta x approaches 0 of delta y upon delta x, or limit as delta x approaches 0 of now this is what we really need. Okay, so the denominator is delta x, but what is delta y? If y is equal to f of x, then what is delta y? So that we get something here. Okay, I'll write that. But compare this to what we did before. We had x1, y1. So instead of that, we have just xy, because we are taking a general point x1 and calling it x. And we want x2, y2. But remember, x2 is just x1 plus delta x. That is x plus delta x. Right? x2 is x plus delta x. And here we are saying y is given by the function f of x. So in the previous example, it was y is equal to x square. So f of x was x square then. So here, more generally, y is f of x. If so, what is y2? y2 is the value of y when x takes the value x2. But so this is, so y2 is actually f of x2. But again, we know x2 is just x plus delta x. So this is actually f of x plus delta x. So here, delta y by delta x is actually y2 minus y1 by x2 minus x1. x2 minus x1 is as before delta x clearly. What is y2 minus y1? According to this, what you have written here, y2 is f of x plus delta x, and y1 is f of x. So this delta y by delta x can be written in this form when you're given y as a function f of x in terms of x. So this is what we define as the derivative of the function y equal to f of x at the point x. Okay, is this explanation clear, or you want me to explain it again? Okay. So this is the definition you have to remember. Again, when we do examples, that you will know how to apply the definition. Okay. So to redo what we already did, or not redo it completely, but just to show you how this fits what we already did. If you take y equal to x square, then dy by dx is according to this it is x plus delta x the whole square, because f of x means x square, right? So this is f of x. So f of x plus delta x is just substituting x plus delta x in place of x. Wherever x is there in the function, just replace that by x plus delta x. So f of x plus delta x is x plus delta x the whole square minus again f of x. So that is still x square divided by delta x. Yes, this is called the first principle method of finding the derivative. Okay, so this is how we find all the basic derivatives in the first place. When you have more complicated derivatives like differentiation of some e to the power of sine x, that requires this approach is not good for that. That requires some other properties of derivatives and other methods that we derive. But initially, before you know anything about derivatives, this is the only thing we can use. So this is called first principle method of finding the derivative. So for simple derivatives, like just polynomials and so on, or just x square, x cube and so on, this is the method with it we use. And once we build a basic sort of table of basic derivatives, we can use them for more complicated functions which are put together from these. When you take a polynomial, for example, you are adding together several terms with different powers of x. And so as we will see from the properties of derivatives, we can reduce that to several different derivatives, each of the form something like this, something like x square or x cube or something. So all of those you'll know from first principles, and then the compound one you can get together by just taking the basic ones and putting them together in a certain way. So the first part of this topic will be just finding all the basic derivatives using this method. Yeah, so this is what we did before. Just to write it quickly, what we get here is x square plus 2x delta x plus delta x square minus x square divided by delta x. Then we cancel these, and then we cancel these, and we're finally left with 2x. Okay. So similarly, if y is equal to x cube, what is dy by dx? So same approach as before. Now, say again, this delta x is just notation. So if it is more convenient for you, instead of delta x, you can take some other variable, simple name like h instead of delta x. It's also a common way of writing it. So in that case, you write h approaches 0, f of x plus h minus f of x divided by h. So the name doesn't matter. You don't. There's nothing to be gained from calling it delta x. It is just a notation to tell us that it is the difference of x. But you can just name that something simpler if you prefer that, because again, when you have x and delta x, it might be confusing when you expand the terms. So here, let me use h instead of delta x. So you can say limit as h approaches 0, f of x plus h. F of x is x cube. So what is f of x plus h? X plus h the whole cube minus f of x, that is x cube, function as it is. Earlier we had divided by delta x. Delta x is being written as h, so it is just h. So this is, we'll write it in the next line. Now x plus h the whole cube. So remember binomial theorem, a plus b the whole cube is a cube plus 3a square b plus 3ab square plus b cube. So here it is x cube plus 3 x square h plus 3x h square plus h cube minus x cube, right? Minus this one, this minus x cube divided by h. You can cancel x cube here. So what remains is 3x square. So you can see that h is common everywhere. So I'll take that out. So h times 3x square h becomes 3x square because you removed one h. 3x h square becomes 3x h, and h cube becomes h square. You've taken that h outside. Denominator is still h. Now these can be cancelled. And so what do you get now? The first term will be 3x square, but here in the second term and in the third term there is h, which is approaching 0. So both of these terms will approach 0. So the limit is just 3x square. So you can compare this. Y is x square, then dy by dx, its derivative is 2x. Y is x cube, it is 3x square. So if it is y equal to x, then what should be dy by dx? Again, those who study differentiation know that this should be 1. Yeah, is 1. Okay. Again, using the same approach, so we'll write h approaches 0. Now, here f of x is x itself. Like this says that f of x equal to x. So f of x plus delta x or f of x plus h is simply x plus h minus f of x, so minus x. Similarly here, x plus h, I'm sorry, this is just delta x, right, which we know is always h. So this is x and x cancel out, leaving h by h is 1. The h approaches 0, that doesn't change. So this is 1. Okay, but this need not really be found as a limit, because y equal to x is what? What kind of curve? It's a straight line. We started with the notion that a straight line has constant slope. So even if you use the generalized definition of slope as the derivative, you will still get the same slope. So y equal to x is a straight line with slope 1. Very clear, right? This is of the form y equal to mx plus c, where this m is 1. C is 0, that doesn't matter. M is 1. So slope of this line is 1. That's all we have found by using our new definition. The point of this exercise is not to actually find the slope, because we already know that, but rather to verify that our new definition of slope, the generalized definition of slope, actually agrees with the special case that we already know. So in the special case of straight line, our new definition should not give us a different value. Otherwise, we can't call it a generalization. Okay. So as expected, we do get the same, because we have not done it in full generality. So we should take a general straight line. General meaning with a general slope, not that ax plus by plus c form, just y equal to mx plus c. And then for this, if you find the derivative, the answer should be m, because this is a straight line with slope m, right? If you check, even if you use the limit, you will get the same thing, because now see, f of x plus h will be, so that is y when x is, the value of y when x is x plus h instead. So you just replace x by x plus h. Everything else remains as it is. Don't write c plus h here. C is a constant. Okay, so only x changes. Minus f of x. So that is mx plus c divided by h. Now c cancels out. So what remains is, so you can see that the mx here also cancels out. So all that remains is mh in the numerator and h in the denominator. Again, they cancel out. So the final answer is m as expected. This is indeed the slope of this line. So it works. Our generalization works because the special case of straight line, it gives the same answer as before. But now, previously we could not, the previous definition, we could not find slopes of this kind of curve where it's not a straight line. Now we can. And again, if you think about it, it makes sense. If it's a parabola, y equal to x square, if it's an upward parabola, as x increases, the slope should increase. And we are getting that the slope is 2x. So as x approaches, as x increases, 2x does increase. Right? So as you go forward on the parabola, you do get larger and larger slope. Same thing with x cubed. As x increases, 3x square, the slope increases. In fact, it increases even faster than this one, which again matches our intuition. If you take higher power of x, that is going to increase much faster. So, yeah, I would like you to do this as an exercise. Take 2 minutes and do this as an exercise. Y is equal to x power 4. Now find dy by dx. So yeah, I think you got the answer, 4x cube. Can you hear now? Yeah, okay. So here again, limit as h approaches 0, x plus h to the power 4 minus x power 4 by h. So x plus h power 4 will be, okay, actually I'll cancel the x power 4. You can see that x plus h power 4, the first term is x power 4 itself, and that is going to be cancelled out. So I'll just write the remaining terms, which is, 14641, right, for binomial expansion of x plus h power 4. The coefficients will be 14641, and then you just start with highest power of x and go on decreasing the power of x, increasing the power of h. We already cancelled the first term, that is x power 4. So the next term will be 4x cube h. Then this is positive, x plus h, so everything will be positive. For 4x cube h, then 6x square h square, 4x h cube plus the highest power of h, that is h power 4, divided by h. So h will cancel out. And the first term is 4x cube, and all the other terms have at least one power of h in them, one positive power of h in them. So they all become 0 as as h approaches 0. So the answer is 4x. So you can see the pattern. When y is equal to x, the derivative is 1. When y is x square, the derivative is 2x. The power is 2, right? Power of x square, the power is 2. So that 2 times x. When y is x cube, it is 3, again the power 3 multiplied by x square, the previous power of x. Similarly, when it is x power 4, it is 4x cube. So in general, you can guess that if you have y is equal to x to the power n, then dy by dx should be this power n is multiplied, and you have x to the power of the previous part, that is n minus 1. So this is just a guess right now. We have to prove this. Okay, so how will you prove it? Yeah, so first principle differentiation. That means what we have been doing till now in these special cases. So, well, I'm going to write proof, but don't think of this as a theorem. We're just deriving the basic differentiation formula. So, in fact, instead of y, I'll write it as specifically x power n. Okay, this is just, instead of y, you can write the actual function here to denote what you mean. So, this is equal to yeah, this is equal to limit h approaches 0. Now what is the function here? X to the power n. So f of x plus h will be x plus h to the power of n minus again f of x, that is x to the power n, divided by h. So in the previous 4 examples we have done the same thing again and again with different values of n. So now we are merely doing it with a general value of n. But now what do you do with this x plus h power n? Do we know anything that allows us to expand this? Yes, binomial theorem, the binomial expansion, right? So this will be, so very carefully expand this. So I'll first write what remains after that, because otherwise later we'll forget that. So if you do the binomial expansion of this thing here, okay, this minus x power n will still be there after that, and then divided by h will be there. So here let's write the binomial expansion. So it is x to the n plus nc1 x to the n minus 1 h plus so on plus h power n. I don't need to write all the terms or the next terms. They will all be of this form, right? You know them. And the last term will be h to the power n. So what is important here is the first and second terms. The first term is clearly going to cancel out with the last term. Okay, we'll write that in the next step. First term is cancelled out, and in all the remaining terms, what is common? You have h here, next you will have h square, and so on. You will have h power n here. So all of them have h in common. So then what you have is nc1 x to the n minus 1 plus, okay, now the next term is also important here. So nc2 x to the n minus 2, actually it is h square. You have taken one h out, so h remains. Similarly, the last term was actually h to the n, 1 has been removed, so h to the n minus 1 h. So these cancel out. Now here every term has h in it. The remaining part, not every term from the second term onwards has h in it. So as h approaches 0, all these terms become 0, leaving only the first term, which is nc1 x to the n minus 1. As you know, nc1 is n. So that proves it, as we expect, as we guessed. Dx to the n by dx is indeed nx to the n minus 1. This is the basic derivative formula. Now this is applicable even if n is not an integer, or even if n is negative. Although that is actually from generalized binomial theorem. Even if n is negative, for example, you will not get exactly this. You will get an infinite series there. But the same thing applies. So we will not do that separately, but take this itself as a result. So this thing needs to be noted separately. As in, you have to remember this for later problems where we are not doing first principle differentiation, but differentiating things like polynomials. So those we'll do later. For now, we'll focus on first principles. So this is one of the most basic ones. What is another simple function? So the first one, then that also is a heading. So now next one is, let's say, e to the power x. In this, the answer is actually interesting. Again, if you already know it, you know why. So I'll leave space for the answer here. We'll derive it. So as usual, we apply the definition. So in numerator, you have f of x plus h. Now f of x here is e to the power x. So replacing x by x plus h, we get e to the x plus h minus e to the x. So actually we should do a series expansion here, but it will not help to do the series expansion in the form of powers of x plus h. So normally if you have e to the power of anything, you do the series expansion of that in powers of that exponent, which is x plus h in this case. That's not going to help here because you'll get increasing powers of x plus h, and for each one you will have to do binomial expansion. So that's very difficult because it's no longer one term like this. You have several terms. Okay. So what we'll do instead is observe that e to the power x plus h by basic laws of exponents is just e to the power x multiplied by e to the power h. And so this e to the power x is there in the first term as well as the second term, right? So you take that common. Then what remains? In the first term, e power h remains. In the second term, 1 remains. Okay. Now, when you are evaluating the limit, it is h that is approaching 0, not x. So e power x is constant. Right? In the function, e power x, x is a variable. But here, x is constant when you are evaluating the limit. So e power x is constant. So one thing is you can, and it's a non-zero constant, so you can take it outside the limit. Even if you don't do that, you keep it inside also, you can see that what matters is this part where h is there. This is actually a limit that we evaluated before. E to the, there we wrote e to the x minus 1 by x as x approaches 0. And we found that the answer was 1, right? So here also we expected this will be 1. If you don't remember the result, you do what we did before, that is series expansion. So you have 1 by h times e to the power h minus 1. So e to the power h is 1 plus h square by 2 factorial, etc. minus 1, this one. Okay. So 1 cancels out. Then after 1 cancels out, every term has h in it. So h also cancels out. Okay. So this h cancels out and becomes 1. So this is actually the second cancellation. And so on. So this is just e to the x. Because everything here becomes 1. This all the other terms remain become 0. Here this only this 1 remains. So derivative of e to the power x is e to the power x itself. That is why this function e power x is so important. It is its own derivative. And it is not just an interesting property. It's important when we, for example, solve differential equations which we obtain when we model some phenomenon in physics or chemistry or any science really, where you have rates of change. Something is changing over time at some rate. Then when you have those rates of change, you get equations involving them, which are basically differential equations, because the rate of change is nothing but the derivative with respect to time. So here we are finding derivative with respect to x. So if you differentiate some function of time with respect to time, that is called the rate of change of that function, the time rate of change of that function. So if you have some process, some chemical process, physical process, where like radioactive decay, for example, where you have some laws of physics or chemistry telling you how the rates, different rates of change are related, you get what is called a differential equation. And so to solve the differential equation, most often you will use, at least the basic ones, most often you will use the exponential function, exactly because of this property. So it's more than just an interesting property. It's actually useful when solving equations involving rates of change, which occur in many natural processes. So we have found two derivatives, x to the power n and e to the power x. Maybe we'll do two more and stop for today. So two other basic functions. Sin x and cos x. So I will write the answer here. So derivative of sin x is cos x. Again, to prove it, first principle approach. Again, we have f of x plus h here, which is sin of x plus h. Now remember, this x plus h is the argument of the function sin. It is the value that is being input to this function sin of x, to this function sin. So you cannot cancel this sin x here with this sin x, because it is not actually sin x in the first term. It's sin of x plus h, right? Please don't think of cancelling it in this way. That is completely wrong. It makes no sense. So what you have to do is expand this sin of x plus h. So remember, what is sin of a plus b? Sin a cos b plus cos a sin b. So here a is x, b is h, sin x cos h plus cos x sin h. Okay, write that separately. It is not the hyperbolic sine function. This is sine of h. Okay, and don't forget this term minus sin x divided by h. But this is more complicated than what we've done in the previous two cases, because nothing actually cancels out. But you do have something common here. So if you take what is common, of sine x times cos of h minus 1, correct? Sine x times cos of h minus 1 remains, plus, this is just the numerator, cos x times sine of h, this term, okay? Separated it because this is taken out. Divided by h. So now what I will do is write the divided by h here and here separately, and this whole thing we are finding the limit of, okay? Now both of these, as h approaches 0, both of these are limits that we have evaluated before. If you remember, sin h by h approaches 1 as h approaches 0, and cos h minus 1 by h. Actually, we didn't do that specifically. We did cos h minus 1 by h square. But what about cos h minus 1 by h? What will happen to that? So we'll find that separately. Okay, we'll find this limit separately, and then just substitute the answer there. How do you evaluate this limit? As before with series expansion. So 1 by h cos h, that is, remember, cos series, cosine series, 1 plus x square by 2 factorial. So here it is h square by 2 factorial. Sorry, not plus, it is minus, alternating. Plus x to the 4 by 4 factorial. So h to the 4 by 4 factorial. Minus, and so on. And then this minus 1 from this minus 1. You want me to repeat? Okay. See, we have reduced this limit to this, or expanded rather. We have two. You can recognize that there are two separate limits here. One is cos h minus 1 by h, and another is sin h by h. The x is constant, so sin x and cos x are constant. What matters is this part. Okay. So we are finding this, we already know. This is going to be 1. So what we do is find this limit separately, cos h minus 1 by h. For that, we need the cosine series expansion. So 1 upon h is here, and then this is the expansion of cos of h. Okay. And then you have this minus 1. So that comes over here. Now, this 1 and this 1 get cancelled. And then in all the remaining terms, you have h common. So after cancelling the h in the denominator, this is left. Minus h by 2 factorial plus h cube by 4 factorial, and so on. But what is the value of this? So what is this limit? It's 0. Yes. This is 0. Earlier, remember when we did this earlier, in the similar problem, we had 1 minus cos of x by x square. That x square made sure that in the first term, whatever was there got entirely cancelled, leaving only a constant. So we got the answer there as 1 by 2. The sign was opposite there. We got the answer as 1 by 2. But now, all the terms have at least 2 h's in them. H square, h power 4, and so on. Right? So that's not entirely cancelled out by the denominator, because the denominator is only h to the power 1. So after cancellation, h still remains in all the terms. So all of them become 0 as h approaches 0. So this limit this part approaches 0, whereas this, as we know, approaches 1. And so the final answer here is sin x times 0, which is 0, plus cos x times 1. So that is just cos x, which proves this. Okay. And so similarly, as homework, take y is equal to cos x. So prove that derivative of cos x is minus sin x. From first principles, prove that derivative of cos x is minus sin.